Today, we're going to decode the language of modern making. It's called Computer Numerical Control, or CNC for short. We're going to explore how a digital idea becomes a physical reality with just incredible precision. Have you ever wondered about that? You look at a solid block of metal, and then you see a super complex, high-performance engine part, and you think, how in the world does one become the other? Well, the answer isn't magic. It's actually a very precise conversation between a computer and a machine. So at its core, CNC is a process that uses digital instructions to control physical tools. A really good way to think about it is like this. Imagine a highly skilled, incredibly precise robot that's just following a digital blueprint to cut or drill or shape a piece of material. So let's break down how CNC actually acts as this bridge and how it translates a design that's on a computer into a tangible object that you can actually hold in your hand. You know, everything in CNC, and I mean everything, is built on the idea of controlled movement. So before we even get into the code or complex designs, we have to understand the physical space that the machine lives in. And most of these machines, they work along three fundamental directions. These three directions are the absolute building blocks of 3D space for the machine, and they're universally known as the X, Y, and Z axes. Now, to keep all of these directions straight, machinists use this really simple but brilliant trick called the right-hand rule. You can actually try it right now. If you make this shape with your right hand, your thumb points along the Z-axis, your index finger points along Y, and your middle finger points along X. It's a universal standard, and it makes sure that everybody, everywhere, is speaking the same physical language. Okay, so this shows us what those axes actually mean on a real machine. The X-axis, that handles movement left and right. The Y-axis moves forward and back. And the Z-axis? Well, that controls the vertical movement, plunging a tool down or lifting it straight up. When you put them all together, these three axes give the tool complete freedom of movement in 3D space. All right, so we've got a machine that can move in three directions. But how does it know where to move, or how fast to go, or what to do when it gets there? It needs a language. The machine needs a really detailed set of instructions, almost like a recipe for a baker. And in the world of CNC, that recipe is written in a special programming language called G-Code. So what is G-Code officially? It's the language that tells CNC machines exactly what to do. It's just a series of commands that control every single aspect of the machine's operation, from its movement and speed to turning on coolant or even changing a tool. I know G-Code might look a little intimidating at first, but it's really just built on simple, logical commands. For example, G00 tells the machine, hey, move really fast to a new spot. G01 says, okay, now cut in a straight line. You can make arcs or use what's called an M code, like M05, to just stop the tool from spinning. Each code is just one clear, direct instruction. So now we've got the physical axes, and we have the language to control them. Let's see how they actually come together in a real-world example. Here is a real line of code from an actual program. Now, this doesn't actually command any cutting. This is what's known as a safe start block. A great way to think of it is like a pilot's pre-flight checklist. Before any cutting starts, this line resets the machine to a known, safe state. It clears out any old settings and gives you a reliable starting point. It's all about consistency and, preventing very expensive mistakes. So let's take a super common task, like drilling a hole. I mean, you could program every single tiny little move. Move the tool over, plunge it down, pull it back up. But for repetitive jobs like that, G-Code has this absolutely brilliant shortcut called a canned cycle. One single command, G81, contains this entire sequence. You just tell it the coordinates and the depth, and the machine automatically does all three steps for you. It moves to the position, it drills the hole, and it retracts. It's just incredibly efficient. And right here, we can see that G81 command in action. It's being used to create these very precise holes you see in this technical drawing, turning that abstract code into an actual physical feature. And to drill the next hole, you just give it a new coordinate, and the machine runs that exact same perfect cycle all over again. And really, that's the whole story in a nutshell. It's all about combining these simple, logical instructions, move here, cut this line, run this cycle, over and over and over again, to build up something that's incredibly complex and unbelievably accurate, whether it's a simple bracket or super sophisticated turbine blade. So the next time you see a precisely engineered object, just remember that hidden conversation that created it. It's a language of coordinates and commands.
quietly shaping the world all around us. And that leaves us with a really fascinating question. As this language evolves, what are we going to be able to ask our machines to create for us next?